In this problem here, we're dealing with a rational function, and all these multiple questions related to this rational function are supposed to help us sketch the graph of this function. In the last eighth part of this question, we're supposed to make a good sketch and understand asymptotic behavior of this rational function. So let me add a page and let's go step by step and answer all of these questions. So the first question is asking about the domain. Well, that shouldn't be difficult because we know that the formula that defines f makes sense for all those real x for which the denominator is not zero. Right? To find these forbidden values, we need to solve the equation x minus 1 equals 0, which of course results in x being 1. So the formula makes sense for all real x except 1. Let me write this down. To find these forbidden values, we need to solve the equation x minus 1 equals 0, which of course means x equals 1. So the domain of f is all real x's except 1. And the first part of this question is answered. Now the second part was about vertical asymptote. Does the function f have any vertical asymptotes? If so, what are they and what are their multiplicities? Well, because it's a rational function has vertical asymptotes for each root of the denominator that is not also a root of the numerator. Recall that a rational function has a vertical asymptote for each root of the denominator. Which is not a root of the numerator. So in our case, the only root of the denominator is 1. And it's not a root of the numerator. Which is easy to check. Right, if you plug 1 here, you get 1 minus 3 minus 1 plus 6, and that's not 0. So x equals 1 is the only vertical asymptote of f. Now, what about its multiplicity? Because x minus 1 is raised to the power 1 in the denominator, it will be of multiplicity 1, and most importantly, our function f will change its behavior near 1. More precisely, if you compute a limit at 1 from the right, so when x is close to 1, the numerator is close to what? 1 minus 3 minus 1 plus 6 is what? 5 minus 3, 2 plus 1 is 3, so it's positive. And the denominator is also positive because x approaches 1 from the right. So there will be positive infinity. And if you compute the limit of f as x approaches negative 1 from the left, it will be negative infinity. So the behavior near this asymptote is different on the two sides of the asymptote. All right, part 3. Use the rational root theorem to find one rational root r of the numerator x cubed minus 3x squared minus x plus 6. Recall what the rational root theorem says. The rational root theorem says that if a polynomial has a rational root p over q, then p divides the free term and q divides the leading coefficient a sub n. The leading coefficient in our situation is 1, so q can only be positive or negative 1, and so p over q will be an integer. So let me write this down. If a rational root P over Q exists, then P divides the free term which in our situation is 6. And Q divides the leading coefficient, which in our situation is 1. Therefore, since P divides 6, P can only be plus minus 1, plus minus 2, plus minus 3, or plus minus 6. And since Q divides 1, it can only be plus minus 1. Therefore, the ratio P over Q can only be, we divide each of these by each of these. Plus minus 1, plus minus 2, plus minus 3, and plus minus 6. If we start computing these values of f at these points, we get what? F, for instance, at 1 is 3, clearly not 0. F at negative 1. Not of f. Not of f. I shouldn't be calling it f, the denominator, computing the corresponding values of the numerator. Let's call it capital F. It's x cubed minus 3x squared minus x plus 6 of f. Let's call it capital F. So here we get negative 1 to the power 3 again 3, which is not 0, fine, and f at 2 will be Oh, that's nice. That's 0. Then we found rational root of the numerator of f is 2. So that finishes part 3. Part 4. Using the root r found in the previous subproblem, find the polynomial g for which the numerator writes x minus r times g. Of course, then g is simply the ratio of this polynomial when it's divided by x minus r. So we find the polynomial g by dividing x cubed minus 3x squared minus x plus 6 by x minus 2. So we get in the first iteration x squared in the next iteration we divided negative x squared minus x plus 6. And in the last iteration, we divide negative 3x plus 6. Therefore, the polynomial g that the problem is talking about is simply x squared minus x minus 3. So that finishes part 4. In part 5, we need to use the quadratic formula or completion of the square to find the remaining two roots of the polynomial g found in the previous subproblem. Right, so we know that 2 is one of the roots of this numerator, and the other roots of the numerator, if they exist, must be then the roots of g. So to find the roots of g, we are asked to use either the quadratic formula or the completion of the square. Either way will do. Let's use completion of the square. So we have x squared minus x minus 3. No need to factor out the leading coefficient because it's already 1. So we treat the linear term as 2 times x times the rest. The rest then must be negative 1/2, because when you multiply 2 by negative 1/2, you'll get negative 1. So the other number in the sum will be negative 1/2. So we must add negative 1/2 squared, and we subtract negative 1/2 squared, so that they cancel, of course. And then this sum here is x minus 1/2 squared. So this is x minus 1/2 squared. And now we need to compute -1/4 minus 3. So -1/4 minus 12/4. That's -13/4. And of course, now using the formula for the difference of squares, remember u squared minus v squared equals u minus v times u plus v. So if you write this as x minus 1/2 squared minus root 13 over 2 squared, it'll be x minus 1/2 minus root 13 over 2 times x minus 1/2 plus root 13 over 2. Or simplifying, x minus 1 plus root 13 over 2, x minus 1 minus root 13 over 2. So we have found the remaining two roots of our cubic polynomial. So the three roots are 2, 1 plus root 13 over 2, and 1 minus root 13 over 2. That finishes part 5. In part 6, we need to go back to our original form of f and divide the numerator by the denominator to express f in the form p plus q over x minus 1. So what we really need to do is divide one by the other with remainder. So we expect the quotient to be a polynomial of degree 2, and the ratio can only be a constant because the divisor is a polynomial of degree 1, and the degree of the remainder can only be smaller than the degree of the divisor. So here I get all right, so the quotient is x squared minus 2x plus 3, and the remainder is 3. So from here I get that the dividend x cubed minus 3x squared minus x plus 6 equals divisor x minus 1 times quotient plus remainder. And therefore, the dividend x cubed, our function f, which is the dividend x cubed minus 3x squared minus x plus 6 over divisor x minus 1 equals x squared minus 2x minus 3 plus 3 over x minus 1. And therefore, remember the question talks about some p and some q. So our p is that quadratic polynomial and q is 3 remainder. And part 6 is now over. All right, now in part 7, we need to complete the square in the polynomial p found in the previous subproblem. So we have p, which is x squared minus 2x minus 3. Again, there is no need to factor out the leading coefficient because it's already 1. So we write the linear term as 2 times x times negative 1. So we see that the other number other than x in the sum must be negative 1. So we add the square of negative 1 and subtract the square of negative 1. So this becomes these three terms are x minus 1 squared, and these are negative 4. So upon simplification, we get x minus 1 squared minus 4. So that finishes part 7. Now part A is the most important. We get to use all of the information we found before to sketch our function f. Well, first of all, we need to write f in two different ways with completely factored numerator and denominator and as p plus q over x minus 1, which we found in part 6. First of all, let's do that. So we know our function is x cubed minus 3x squared minus x plus 6 over x minus 1, which will be, when we factor the cubic, it'll be x minus 2 times the other two roots we know are this and this, so they will be x minus 1 plus root 13 over 2, x minus 1 minus root 13 over 2 over x minus 1. And the other way to write f we know is x minus 1 squared minus 4, that's p, plus q, which is 3 over x minus 1. Writing f this way, in two different ways, allows us to complete the rest of part 8. We can immediately find all x-intercepts and their multiplicities. We can immediately sketch all vertical asymptotes, and we can determine the asymptotic behavior of f when x approaches positive or negative infinity. All of this can be easily derived from writing f this way. So let's summarize what we have. Well, first of all, 3 x-intercepts. Two, 1 plus root 13 over 2, and 1 minus root 13 over 2. All are of multiplicity 1. Now, we know there is only one vertical asymptote at 1. It's also of multiplicity 1. And finally, the behavior at infinity. It's easily derived from this part. You see, when x approaches positive or negative infinity, this portion becomes essentially 0. And so our function will be approaching p, this parabola. So when we sketch our function f, it will make sense to first sketch the parabola x minus 1 squared minus 4. Since 3 over x minus 1 approaches 0, our function f approaches the parabola p, which is x minus 1 squared minus 4. And so when we do our sketching, it makes sense to first draw that parabola. So where is that parabola? X minus 1 squared minus 4. All right. Let's start sketching. All right, so let's start with the parabola. What do we know about it? It's pretty much the parabola x squared, which is first shifted by 1 unit to the right, and then shifted 4 units downward. Maybe I should use x minus 1 squared minus 4. Okay, so let's say this is 1, -1, -2, -3, -4. And so that's our parabola. Roots are 3 and -1. Now, where is our function? So roots of our function are 2, and so 2 is here, and 1 plus root 13 over 2. Where is that? So this number is negative. This number is positive. I want to know, how do 2 and this other number, 1 plus root 13 over 2, compare? So multiply by 2. So we see immediately that 2 is less than that number, 1 plus root 13 over 2. But I also want to know how that number compares with 3. So how do 3, because 3 is also an important number. So clearly we get that 3 is greater than that number. So 1 plus root 13 over 2 is between 2 and 3. So one root is 2, the other root is here, I don't know, somewhere here. The other root is 1 minus root 13 over 2, and I want to know how that number compares with negative 1. So how do negative 1 and 1 minus root 13 over 2 compare? So multiplying by negative 1, we change the sign. So we get 2 comparing 1 plus root 13. So that's 1 versus root 13. And of course, 1 is less than root 13. So this here is less, this is less, this is less, this is greater. So negative 1 is greater than that number. So just for the sake of precision, I want to know how that number compares to negative 2. So negative 2 this was a mistake here. Let's do this again, more carefully. So I have negative 1 versus 1 minus root 13 over 2. So that's negative 2 versus 1 minus root 13. So multiplying by, so that's negative 3 versus negative root 13. So that's 3 opposite sign, root 13. So 3 is definitely less than root 13. And the result still is that our root is to the left of negative 1. Now, how does it compare to negative 2? So we get negative 4 versus 1 minus root 13. So that's negative 5 versus negative root 13, of 5 opposite sign root 13. So of course 5 is greater because 25 is more than 13. So greater, greater, less, less, less. So our number 1 minus root 13 over 2 is between negative 2 and negative 1. All right, so let's say the root is here. We also need to show the asymptote, x equals 1. So this is the graph of P, x minus 1 squared minus 4. And remember that at infinities, our rational function should really get close to the parabola. Also, we know that maybe another point here, behavior near the asymptotes on the right from 1. Our function is positive infinity, and to the left of 1, our function is negative infinity. So we can kind of start drawing. To the right of 1, we have positive infinity. Then we have these two zeros. Then our function should get closer and closer to this purple parabola. All right. Now, to the left of asymptote 1, our function is negative infinity. I would also compute f at 0, by the way. What is f at 0? So again, remember our function. Well, you can use this formula. So 0 minus 1 is negative 1. Negative 1 squared is 1. So that's 1 minus 4 plus 3 over 0 minus 1, which is what? Negative 3 plus 3 over negative 1, which is negative 3 minus 3. That's negative 6. So our function passes through the point negative 0, negative 6. All right. Now, it starts at negative infinity here. Will pass through the point negative 6. Will pass through this 0. And then we'll approach the purple parabola again, because it's asymptote at both positive and negative infinity. So something along the lines of this. Again, this root here is 1 plus root 13 over 2. This is 2. This number here is 1 minus root 13 over 2. This is the purple parabola x minus 1 squared minus 4. This line is x minus 1. The red graph is our function f. And that's how it looks like. Again, it was very helpful to have our function f written in this form, because when x is huge, positive or negative, this part is negligible, and we are left with the parabola x minus 1 squared minus 4. We know the behavior near the asymptote, positive on the right, negative on the left. We know the 3 zeros, all are crossings of multiplicity 1. And that finishes this problem.